Okay, so far we've talked about sets of numbers. Well, let me just review kind of where we're at. We said we're going to assume naive set theory. Okay, and then we basically said we're going to assume we know what the natural numbers are, that we're in agreement on the properties of the natural numbers. Now, if we had wanted to, we could have used our knowledge of, the set theory that we're assuming to actually build the natural numbers. Okay, and the way we would have done that is we would have said, I'm going to do this over here on the side. We would have said, like, well, 0 is the same as the empty set, and then 1 is the same as the set containing the empty set. And then 2 is the set containing the empty set and the empty set, and things like that. Okay, we could have actually built the natural numbers. It's a weird kind of set theory way to build the natural numbers. And then once you build the natural numbers, you basically get the integers for free. Okay, you just allow them to be negative and 0. And then once you've got the integers, you basically get the rationals for free. Okay, so again, we didn't build any of these, but I'd like you to grant me that we could have, if we had wanted to, built the natural numbers and then used that to build z and q. Okay. In contrast, for the real numbers, we said this is tricky. Okay, and it really is kind of tricky to build them out of these smaller pieces, and we're not going to do that in this course. Okay, so that's the real contrast here, is that we're not even going to try to build these. So what do I mean by that? I mean, the other ones we could at least build them out of simpler pieces, but the real numbers, it's tricky and we're not going to do it. Basically, we're just going to agree on the properties that they satisfy. Okay? Now, the problem with doing that is that there's a lot of properties satisfied by the real numbers, and we would never come up with an exhaustive list of here are all the things that the real numbers satisfy. Okay? I mean, basically, we're talking about, that's almost saying, all of calculus and everything. So what are we going to do? We're going to agree on some axioms, and then we're going to study some obvious consequences of those axioms. Okay? So we're going to agree on axioms of R. Let me be careful here. We're not really going to agree on what the axioms should be. We're just going to take the book's axioms. We're going to agree that R satisfies all of those. Okay? And then we're going to look at simple consequences today. Okay? So that's the goal of today's lecture. Let me know. Jump in now if you have any questions. So this is section 2.1 in the book. If this were a lecture on a chalkboard, which would be great normally, but then I would really struggle to present this material because there's just so much to present, and it's not very deep. So anyway, I actually just took some screenshots of the book. So the key is I'm going to have to skip over this section. I'm going to cover the whole section today in the next 40 minutes, hopefully. And it's good to read it. It's good to work through it. It's good to see how we can derive these things from the axioms. but it's not terribly surprising, or I'll forgive you if you don't find it interesting even. It's a little bit dry to do this. Okay, so before we get started, I'm going to write down the kind of definition of R. It's a complete ordered field. Okay, every one of these words is important. Field is a term from abstract algebra. Okay, in abstract algebra you study rings. A ring has two operations, addition and multiplication, and it satisfies a bunch of axioms. Okay, a field is a special type of ring where you can also divide. Okay, so this is an algebraic term. Ordered. Well, the ordered part says, in abstract algebra, there are lots of fields, but the real numbers are special because they come with the real number line. So we can actually put the real numbers on this line and we can talk about less than or equal to. That's the ordered part. And then complete. Complete means that there are no gaps in that real number line. Okay? So these first two are actually going to be satisfied by the rationals. Well, sorry, they're the last two as I wrote them. They're the first two as I talked about them. The rationals satisfy both of those. The rationals are a field and they're ordered. They don't satisfy the completeness. Okay? So what we're going to do today is the field part. So this is section 2.1. And then let me just check. Yep. The order part. Oh, I'm sorry. There we go. We're also going to get to the order part today. And then we're going to do it more in section 2.2. And then in 2.3 and 2.4, we're going to talk about the complete part. Okay? So there's three big things for the real numbers: complete ordered field. We're going to start with field. And for each of these three things, we have a set of axioms. Okay. So let's look at what are called the field axioms. Oops. There we are. Okay, your book has them all laid out as the algebraic properties of the real numbers. So we have two operations, addition and multiplication. You might notice we don't have subtraction here. That's because subtraction is just the opposite of addition, and we don't have division because it's the opposite of multiplication. So we just need to talk about these two. Okay, all of these things are they're things we've always learned to use. Addition is commutative. Addition is associative. There is a zero, so we add zero to something, we don't change it. And every real number has a negative. And if we add the negative to the real number, we get back to zero. Okay, that's the addition. And now we get into multiplication. It's also commutative. It's also associative. It also has an identity. This time it's 1, and we multiply anything by 1, we get it back. And then we have inverses, except we don't have an inverse for 0. But every other real number we can divide by. Okay, and the way we write it in the axioms is that means it has a multiplicative inverse. Okay, that's it for the multiplication axioms. And then the final axiom is the distributive law, telling us how addition and multiplication interact. Okay? That's it. Those are the 9 axioms that we assume about the algebraic structure of the real numbers. And you'll notice they're the same 9 axioms we assume about any field, okay, in abstract algebra. Are there any questions about these before we go on to, we're going to derive a couple easy things from them? Anyone?
No, I have one question.
Go ahead.
Is okay, never mind. I was going to ask about closure, but that's assumed in the binary operation.
Right. So, right, we don't assume that, we don't specifically say if you add 2 real numbers, you get another real number, because that follows from the way we've kind of set it up here. That they're both binary operations. So that means they have to map from pairs of real numbers to another real number. Yeah, but that's a good question. Some abstract algebra books will actually spell that out. Okay. Oh, and I guess I should point this out. Abstract algebra is not a prereq for this course. I just know that several of you have had it. If you haven't had it, that's fine. Just when I say abstract algebra, just ignore it. Okay? This will be newer to you than to other people, but you don't actually need to know any abstract algebra theorems or anything. Okay? So these are the 9 algebraic, the book calls them properties. They're really the axioms that we agree on. So we're going to agree that in all of our heads, we each have a version of the real numbers, but it satisfies all 9 of these things. Okay? Now, let's look at a theorem that we can derive from these. Let me put the theorem at the bottom. Yeah, I'm never going to fit these both in the same. Okay. Here's something you can prove. Part A. If you add something, oops, I wanted, there we are. If you add something to a real number A, and you get back A, then the thing you added was 0. Okay? What part A is really saying is that the 0 of the real numbers is unique. Okay? Not surprising, right? B is saying the same thing about the 1 of the real numbers. If you multiply a real number by something and you get back itself, then you multiply by 1. And C is saying if you multiply a real number by 0, you get back 0. Okay? Now, we could all just say, yeah, our real numbers satisfy this, right? Because the real numbers that we have in our heads satisfy all 3 of these things. So we could just say, let's add them to the axiom list. Except that's not the modern axiomatic approach to mathematics. Our goal is to have our axiom list be as short as it can be, and then to derive everything else from that list of axioms. So the point is these follow from the axioms, so they don't need to be axioms. They can be theorems. Okay? Now, your book proves all these things. Again, we'll never make it through this section today if we do it for all of them. But I just want to give you an example. So let's prove part A. Okay? And I'm going to try and squeeze this proof right in between them. Okay. What would our proof be? Well, for any real numbers, A and Z, okay, Now, let me add a disclaimer here. I don't think I don't think this proof is incredibly easy to come up with on your own. You kind of have to stare at these axioms for a while to see what you're going to use and what order you're going to use it in. So I'm going to present a polished proof because I stared at these axioms for a while, right? It's tough to get it this polished, but okay. And I'm also going to put proof in quotes. Usually a proof is written in complete sentences. I'm going to take some abbreviations here, just to fit it in the space that I've allotted it. Okay, so I'm just going to get a string of equalities. Oh, and I guess I need to state our hypotheses. So our hypotheses are that if this happens, so if z plus a equals a, then what? Well, we want to end up with z equals 0. So now we're just going to do some tricks. I'm going to say z equals z plus 0. Okay. Why am I allowed to do that?
Because of axiom A3.
Good. A3. Okay. Cool. And now that is equal to z plus a plus minus a. Okay. That's because of a4, because a plus minus a is equal to 0. Okay. Good. Now I'm allowed to regroup those by the associative property, which will be a2. We can write this as z plus a plus minus a. Okay. Now, by our hypothesis, z plus a is equal to a. So this is a plus minus a. And now we know that a plus minus a, according to a4, is equal to 0. So that's the end of the proof. Okay. We started with our hypothesis that z plus a equals a, and we concluded that z is equal to 0.
So there isn't a certain number of axioms that you need to like hit. It's just like that was just like algebraically. So like now it's just canceling, and you can like clearly see that z equals a minus a, which is like equal to 0.
Right. Right.
Okay.
Yeah, we certainly don't need to use all the axioms if that's your question. We just use the axioms we need.
Could you have just started off by moving a to the other side and just saying that was axiom 4, like making z equal to a plus negative a?
Oh boy. Let me think about that. So what you're saying is what's called the cancellation property? That I can add the same thing to both sides?
Yeah, kinda.
Man, we're so yeah. I mean, I guess if we're going to assume the cancellation property, I think we should actually prove the cancellation property if we're going to use it. Um, you know, let me just say, this deriving the things from the algebraic axioms of real numbers. This is not my favorite thing in the world to do, and you'll notice it's not on your homework. Okay, and it's not going to be any quiz. Okay, I just wanted to, I have to show you one example of how it can be done. And, basically after this section, we're just going to say, yep, that can all be done, and we agree that these things are all true for the real numbers, and, let's move on, right? You're never going to have to break things down into those axioms on the homework or the quizzes, okay? Or in real life either, I promise you. Okay, I'm just showing you that it can be done. We can use this axiomatic approach to derive these properties of real numbers. And these are the 9 that we need to get all of our algebraic properties. Okay? If we had to prove... Oh, go ahead.
So on the homework, we're allowed to use the cancellation property, for example.
On the homework, you're allowed to use what I would just call algebra. Yeah.
Okay.
Right. Yeah. On the homework, you'd say, z plus a equals a. Yeah. So I mean, you just say so z equals 0. I mean, right. This is not a theorem you're going to reference ever. Okay. We're just showing you how you can get these consequences from these axioms. Okay. So, if you're taking notes, I think it's perfectly reasonable if your piece of paper is completely blank up to this point today. Okay, because you don't need to write any of these axioms down, and these consequences, I hope you know them well enough that you don't need to write them down either. Okay? Now, if we were to prove B, it'd be the same thing, basically, except we'd have to be a little bit careful that B isn't 0. And then we'd be using the multiplicative properties instead. And then to get C, we actually have to use the distributive property. Okay. So these are fun little puzzles. You can try them by yourself. You can look in the book, or you can just move on. Okay. Now, here's another consequence. These start to get a little bit more, I don't know if more interesting isn't the word, but they start to get a little bit harder to derive. If A is not 0 and A times B equals 1, then B really is the multiplicative inverse of A. Okay? So that says that, in our axioms, let me just go back up here real quick. What did our multiplicative axiom say? I'll circle it here. That's not the one I wanted. That one. Okay. M4 says that if you're not 0, there does exist a multiplicative inverse or reciprocal. Okay. What M4 doesn't say is that thing is unique, that there's only one. And the point here is that it doesn't need to, because you can prove it, and that's theorem 2.1.3a. Okay. Now, part B is a little bit more interesting. If A times B is 0, then either A is 0 or B is 0. Okay? we agree our real numbers have this property, right? I'm going to skip the proof of this theorem. For those who have had abstract algebra, this means there are no zero divisors, but we know fields can't have zero divisors. So, oh, and I'm sorry, I realized I skipped a question from chat. Would this be an acceptable proof on a homework? Well, I'm not going to give you a problem like this on the homework, but no. No, I have to say that this would not, what I wrote here would not be an acceptable proof. If you want to see an acceptable proof, look in the book, where basically what they say in the book is they write it in complete sentences, and they say, using A3, A4, A2, the hypotheses, and A4, we have, and then they write out the string of equations. Okay, that's how you would write it using a complete sentence. It's just, you know, when I'm writing on the whiteboard, I'm trying to show you each step one by one. It's nicer to I think do it this way. Okay. So one thing that's going to keep coming up is that the proofs that you write, well, any proof in mathematics, it should not be your first draft of the approach. So you figure out how you're going to get the conclusion you want, and then you basically rewrite it, almost working backwards. Okay. So obviously the proof in the book is not something you would write. You wouldn't write, say, you know, using A2, A3, the hypotheses, and then A4, we get the following. You would have figured it out first, and then you write that. Okay. So, we have this theorem, which again, I'm not going to prove. We already mentioned subtraction. The axioms and the theorems don't need to mention subtraction because it's just adding the negative. But we're going to use the symbol. And division, again, the axioms and the theorems don't mention division because it's just multiplying by the reciprocal. But we're going to use division. We're also going to use exponents. So for n a natural number and a in the real numbers, we have a to the 1 is a, and a to the n plus 1 is a times a to the n for n at least 1. Okay, we all know that. Notice what we have not defined. We have not defined fractional exponents or real exponents. Okay, we're going to suspend the definitions of those for now. Okay. We can also, a to the 0 is 1 unless a equals 0, and then we're not going to define it right now. Okay? Kind of depends on the context, what you really want that to be. What you want 0 to the 0 to be. Okay? And finally, we can write a to the minus n for 1 over a to the n. Okay. We take this all for granted, but, you know, back when Newton and Leibniz were inventing calculus, they did not have exponent notation. So they would have to write an equation that looked like 5xx plus 6xx, etc. They didn't have that notation. Okay. Any questions on that? No? That's the field part of the complete ordered field. Now we move on to the order part. Okay. Now, the ordered part starts out without any reference to order. Okay. And this is a little bit weird. Okay, so this is quite possibly new to everyone, including maybe even myself, presenting it this way. So we're going to start out by defining the positive reals. We're going to use this notation, or at least the book is going to use this notation, P. A lot of other people, and I probably will do this too, use R plus for the positive real numbers. Okay. Now, in your head, you're thinking about the positive real numbers. You know what they are. Just verify that your positive real numbers satisfy these rules. If you add two positive reals, you get another positive real. If you multiply two positive reals, you get another positive real. And given any real number, either it's a positive real, or it's negative as a positive real, or it's zero. One of those three things has to happen. So this presents a trichotomy. Okay, now these are the axioms that we're going to use to get our order out of. Okay, so we all agree our real numbers satisfy these three things, and now we're going to study the consequences of those three things. Now, I guess the point before we get to those consequences is that these three axioms allow us to make a definition. Okay. Let me, this one came out crooked. Is it that tool? Aha. There we go. Those three axioms allow us to make this definition. We're going to define, let me emphasize that we're defining less than. Defining the order less than. If A minus B is positive, that means that B is less than A. Right? So we're going to define B less than A if A minus B is positive. Okay. If A minus B is positive or 0, we're going to say B is less than or equal to A. So I guess I should add. We're also defining less than or equal to. Okay. Now, it might not be immediately obvious that this is exactly the same less than that you're used to. That it really captures all of the order relationships among the real numbers. But I think I'll have to leave you to think about that a little bit. This really is the order we're used to. Okay. Now, we look at this trichotomy property, which is really important. And instead of A, think about putting A minus B in there. We see for any A and B, real numbers, we have A minus B is positive, or A minus B is 0, or minus A minus B which would be B minus A, Did not want to do that. Okay. And why did I write R over here? Right? Okay. Now we translate these three conditions into the order, and what do we see? This one, if a minus b is positive, then b is less than a. Or if a minus b is 0, then we know a equals b. Or if b minus a is positive, then it's the reverse. It's a is less than b. Okay. So we've also got a trichotomy law for our order. Given any two real numbers, either one, the first is less than the second, or they're equal, or the first is greater than the second, right? Okay, these are obvious things, just seeing how they follow from these three axioms of the positive real numbers, actually. So again, we're saying the positive real numbers satisfy three axioms, and therefore we can define this order. And now we're going to see the consequences of that. Take any three real numbers. And this first consequence is transitivity. So let's see. We have on our real number line, we haven't talked about the real number line, but I'll just draw it to illustrate this. A is bigger than B, and B is bigger than C, and therefore A is bigger than C. Okay, that's transitive. I'm a little bit embarrassed by this. I don't know the name for the second rule, so interrupt if you do. But we can add the same quantity C to both sides of an inequality and keep the inequality. I don't know the name for that. And now, the most interesting one, if you were going to prove any of these, which we really do not have time for anymore today, would be C. Now, C is saying, and there will come a time when most of you will make this mistake in this course, in your homework at some point. So just remember this one. When you multiply by a positive real, you keep the inequality. But when you multiply by a negative real, you switch the inequality. Right? So these are all consequences of our definition and those three axioms of the positive real numbers. Okay. Any questions? Sorry, we're having to go through the end of this section pretty quickly. I do want to show you, I think, one more proof here. And it's going to be on the next consequence. So, do I have room? Yeah.
Maybe a stupid question about the last one. So if C is equal to 0, then you say that 0 is greater than 0 and 0 is less than 0, or is there?
Mm-hmm. So C cannot be 0.
Okay.
Right, so that's not allowed in that statement.
Okay.
And we all know if you multiply both sides of an inequality by 0, you get a nothing, right? Right. You would never want to do that because you just lose all information that you had in the inequality.
I have one question about the positive reals.
Mm-hmm.
Feel free to skip it. How do we know that we're getting the same positive reals that we're used to? That there isn't another positive reals? And feel free to skip that one because it seems like it's
No, that's okay. That's a good question. And we don't. Okay, we don't. So you know, this is the classic like stoner question of what if, you know, when I see red, it's your green, right? So as far as I'm concerned, your real number line might be the opposite of mine. Okay, but that could be the only difference between our two real number lines, is that yours might be opposite of mine. So this actually, you know, to use an algebra term again, this does not determine the real numbers. It determines the real numbers up to isomorphism, but it doesn't like tell you which side is the positive one and which side is the negative one. Okay. So you can also think about that as kind of an arbitrary choice that one side of the real number lines will be called, of the real number line will be called the positives. And then it's sort of like when you multiply by a number on the other side of the real number line, then you go to the other side. Okay. Right, so I wanted to look at, here are these consequences. B is hilarious. Oops, let me undo that. I hope we agree that B is hilarious. 1 is bigger than 0. And I think A is also a little bit interesting. A says if you square a non-zero number, you'll get something bigger than 0. Okay. And then C says all of the natural numbers are bigger than 0. Okay. Now, I do want to spend a little bit of time on this. I realize we've only got a couple minutes left, but let me first dispense with C. C you get by mathematical induction, assuming B. Okay. What do? Well, 1 is greater than 0, and then you can add to both sides. A is the one I wanted to talk about. Now, if you know anything about complex numbers, and hopefully you at least know that there are complex numbers, and there is this imaginary number I that's the square root of -1, that conclusion does not hold for complex numbers. Okay, I is not equal to 0, but yet its square is -1. So what axioms do the real numbers satisfy that the complex numbers don't?
Is it the ordering?
Yeah. Yep. The complex numbers don't have an ordering. Yeah, I see it in chat too. Thank you. Oh, I also see a question about quizzes being timed. Yeah, we'll talk about that next week. And yes, I do want complete sentences on your quizzes, but we'll talk about it next week. Okay. To prove A, let's just talk really quickly. If A is positive, then if we go back up, if it's positive, then we have 215B. If A is positive, then A and A are both positive, so A squared is positive. And we're done. Okay? On the other hand, if A is negative, then minus A is positive. So A squared, which is minus A times minus A, is positive. Okay, that's by the earlier part. Now, again, since we're at this level of detail, you might ask, how do we know that a squared is minus a times minus a? Well, you go back now to the algebraic properties. And the algebraic properties of the real numbers will tell you that a squared is minus a times minus a. Okay? So, I guess I'm going to conclude with the following very, very important theorem. Okay? There is no smallest positive real number. Okay? So this theorem technically says if you have a real number that's non-negative and less than epsilon, for every positive epsilon, then your number had to be 0. Okay? And I just want to quickly sketch the proof. Suppose, to the contrary, that a were greater than 0. Then, well, what would be true? Well, then a over 2 would be between 0 and a. Okay. Now, please nobody ask me which exact axiom that follows from. Okay, but I hope we can agree that that's true, right? So setting, if we took an epsilon naught to be a over 2, then, well, what does it mean? It means that epsilon naught is less than a, but epsilon naught is greater than 0, and that's a contradiction. And just to be clear, that's a contradiction to our hypotheses. Okay. Let me just say, we basically made it through section 2.1, except, well, there's a couple more things. If you multiply and you get a positive number, then either both parts were positive or both parts were negative, okay? We all agree that's true. There's a proof of that from the axioms. As a corollary, if you get something negative, then, well, one of them was positive and the other was negative. Okay? That's just a direct corollary of that theorem. And then what I was going to do, okay, thank you. What I was going to do, if we had time, was derive a few things. So I'd encourage you to look in the book. You can get the arithmetic geometric mean equality out of what we've got. And you can get this thing called Bernoulli's inequality out of what we got. Now those aren't things I would ever expect you to have memorized for this course, and I really don't know if they're going to come up, but they're neat, actually non-trivial things that you can prove based on all the properties of real numbers that we have established, or that we've said we could have established today. Okay, so I'm going to end class right now because we've run over, and I will stick around for any questions that you have. Okay, so feel free.